I am Ryan Truen, a graduate student at the Georgia Institute of Technology, and this is a presentation on the automated reconstruction of control logic for Programmable Logic Controller Forensics. Before I start, I'd like to acknowledge the original authors of this paper, Syed Ali Kazem and Irfan Ahmed, both of Virginia Commonwealth University, as well as Juan Lopez of Oak Ridge National Laboratories. This paper was presented at the 22nd Information Security Conference in New York, in September of 2019. The link to the original paper is provided below. This paper presents Similo, an autonomous scalable virtual PLC framework for forensic investigations of denial of engineering operation attacks, also known as DEO attacks. DEO attacks were identified in March of 2018. These attacks cause a loss of situational awareness of automation equipment. There have been 3 types of attacks identified, and due to the deceptive tactics employed, standard recovery efforts are not effective. So how applicable are these attacks to industrial control systems? Industrial control systems are often considered highly targeted systems due to their potential to impact a critical infrastructure, such as electric grids, defense manufacturers, or even transportation systems. Additionally, because of cost and uptime requirements, industrial components such as historians, human-machine interfaces, programmable logic controllers, and engineering software are not maintained and patched like they would be in a traditional IT system. In the past, network segregation was considered a sufficient defense against cybersecurity attacks. But with the growing need to access large amounts of data that is generated by these systems are becoming increasingly connected, making them more susceptible to cybersecurity attacks such as these DEO attacks. Before I dive into the framework, it's important to have a good understanding of control logic. Control logic is logic that is executed on the Programmable Logic Controller, or PLC for short, to control a process or many processes. To develop control logic, an engineer uses an engineering software such as CODASPY, Schneider Electric's So Machine Basic, or Allen Bradley's RS Logix 500, just to name a few. Regardless of the engineering software, the flavor of control logic that they use will most commonly be one of the 5 languages defined by IEC 61131-3. This could be textual-based languages such as instruction list, structured text, or graphical languages such as ladder logic, function block diagram, or sequential function charts. It's important to note that while the high-level source code is often in a common language defined by IEC 61131-3, the code must first be compiled into binary control logic, which varies between both vendors and PLCs, before being stored into the PLC's memory and executed. To store and execute the binary control logic files on the PLC, a download must occur. Downloading is the process of transferring the binary control logic files from the engineering software to the PLC's onboard memory. When the PLC is placed in run mode, the binary control logic will then be executed. To extract the binary control logic from the PLC, an upload must occur. The upload transfers the binary control logic files from the PLC to the engineering software. Once the files arrive at the engineering software, they are then decompiled back into their high-level source code. The act of downloading or uploading can be performed either locally by connecting the PLC directly to the computer, or remotely by placing the PLCs on a network accessible by the engineering software's host. Pictured on the right is an example of a common ICS architecture. This terminology is specific to Siemens, but it serves as a good representation. The engineering system is the computer or server that hosts the engineering software. The automation systems are synonymous with PLCs. Other components, such as the OS servers, route control servers, and their respective clients, are also shown, but they are of less interest to us for this presentation. What is important is that we note the remote connection between the engineering software and the PLCs as shown with a red line. Keep this connection in mind as I continue throughout this presentation. Now that we have a better understanding of control logic and the transfer process between the engineering software and the PLC, let's discuss the denial of engineering operation attacks. In DEO Attack 1, when an engineer attempts to download the control logic, an attacker will utilize a man-in-the-middle attack to capture the binary control logic, infect it, and then send it to the targeted PLC. This program could be infected by altering parameters such as motor speed set points, PID constants, preset times, or any other system parameter that the attacker deems appropriate. In addition to this attack, when the engineer attempts to upload the logic from the PLC, which is common when troubleshooting, the attacker will send the original binary control logic back to the engineering software. When the engineer looks at the decompiled program, they will discover that the PLC is showing the logic they have intended to download, but not the logic that is currently running on the PLC. DEO Attack 2 is similar to DEO Attack 1 during the download phase. The engineer downloads the files to the PLC, the attacker infects the program and passes it on to the PLC. But this time, when the engineer attempts to upload the logic from the PLC, the attacker will modify the binary control logic in a manner that will cause the engineering software, or at least the decompiler, to crash. So how do you detect a DEO attack? Because the upload process is rendered unusable in determining the logic that is executing in the PLC, the logic would need to be investigated by capturing the network traffic. To decompile the network traffic into its high-level source code, a decompiler would need to be created. This was actually performed with ladder logic on a MicroLogix 1400 in the paper released back in March that initially identified the DEO attacks. They created a tool called Lattice. While Lattice was a success, its development was very labor-intensive, and for every PLC type, a new decompiler would need to be developed, thus making Lattice unscalable. An ideal forensic tool would be both autonomous, meaning no manual reverse engineering required, and scalable, meaning compatible or easily adaptable at least to other PLC types. By capturing network traffic, it was found that the upload process is deterministic. When the upload request is sent from the engineering software, a series of unique requests are sent to the PLC, and the PLC responds with the same messages. What this means is that if you know how a physical PLC will respond, you can replicate that in virtual form. This is the basis in which Senthivel functions. Because Senthivel needs to be scalable, this process was repeated on 3 PLCs, a MicroLogix 1100, a MicroLogix 1400, and a Modicon M221. What was found is that the fields in the header change between messages, sessions, and PLC types, not just in content, but also in length. Because Senthivel needs to be autonomous, it needs to be capable of determining both the location and content of these dynamic header fields, while also maintaining a high level of accuracy. If the dynamic fields can be captured and the packet headers can be modified, the logic can be passed back to the engineering software decompiler, avoiding the need to create a decompiler for each type of PLC and for each type of high-level source code. To accomplish these tasks, Senthivel utilizes a learning phase and a testing phase. To start the learning phase, multiple PCAP files of an upload of non-infected and identical binary control logic files are needed. In the report, they started with 2, called PCAP1 and PCAP2. The first step in the learning phase is pairing. Pairing is performed by pairing the request from PCAP1 with its respective request from PCAP2, as well as the responses in PCAP1 with the respective responses in PCAP2. To find the same message, both the message length and the similarity of the content are evaluated. The content similarity should be pretty high because the control logic is identical. The second step in the learning phase is comparison and grouping. During comparison and grouping, differential analysis is performed on the identified pairs to determine the location of the dynamic fields. Additionally, because the header size changes, the indices of the header location will change. To keep the indices the same, the messages are grouped based on header size. The last step in the learning phase is optimization. In the optimization phase, the indices are compared across grouped messages. Then if the indices exist in more than 50% of the messages within the group, the indices are grouped and identified as a dynamic field. At this point, the process can repeat with the addition of more PCAP files, and using the majority rule described in the optimization process, the results will be grouped again, creating the learning phase dynamic fields. After the learning phase dynamic fields have been identified and located, Similo is ready for the testing phase. During the testing phase, a target PCAP file is loaded into Similo. The target PCAP file gets loaded into a database as pairs of requests and responses. Once loaded, the communication server starts, then waits for an upload command from the engineering software. Once the upload command is sent, a request hits the communication server and gets redirected to the identifier. Much like the pairing operation in the learning phase, the request is compared by message length and message content to find the most similar match. Additionally, the identifier also identifies the dynamic fields of the testing phase. The testing phase dynamic field and the learning phase dynamic fields are then compared in the field analyzer. In the field analyzer, if the dynamic fields in the testing phase are contained within the learning phase dynamic fields, there is no change made to the indices of the dynamic fields. If the dynamic fields are identified adjacent to or overlapping, the dynamic fields are combined. The results of the field analyzer are then passed to the reconstructor along with the initial request and the request and response messages found in the identifier. Once the reconstructor has the response and the dynamic fields, the response can then be morphed into a valid response to the request from the engineering software. This process is repeated for each request until the binary control logic is successfully passed back to the engineering software, where it is then decompiled into its high-level source code. To implement Similo, the developers utilized many existing tools that had already been created. For packet manipulation, the developers used Scapy. For calculating similarity in instances such as pairing and identifying, Sequence Matcher from the difflib library was used. Socket library was utilized to open ports that are known to be used by the PLCs that were being tested. Port 48818 for the Micrologix PLCs and port 502 for the Modicon PLCs. The identifier, reconstructor, and field analyzer were all created by the developers as functions in Python. For evaluating Similo, the following process was performed. The lab setup consisted of a Windows 7 VM to run the engineering software, so Machine Basic and RSLogix 500, 3 physical PLCs consisting of a Micrologix 1100, Micrologix 1400, and Modicon M221, and a Ubuntu VM for running Similo. To evaluate the functionality of Similo, network traffic was captured for the upload process, and then software was compared with the original code manually. The dataset of control logic used varied in both complexity and source code type, namely instruction list and ladder logic. For Similo to act as a virtual PLC for forensic purposes, it must be capable of performing 3 tasks. It must be capable of establishing a connection with the engineering software. It must maintain the connection, and it must correctly transfer the control logic to the engineering software. To test the transfer accuracy, 22 Micrologix 1100 files, 39 Micrologix 1400 files, and 52 Modicon M221 files were uploaded to Similo. The table provided shows that the content output by Similo matched identically to the original program. Additionally, in each of these 113 files, the engineering software was able to discover Similo and maintain a connection for at least a few minutes while the uploads occurred. Because Similo uses previously learned responses to the requests made by the engineering software, it is crucial that the messages be accurate at the packet level. In the report, a table was provided that shows the accuracy of the packet database with respect to the request made by the engineering software. From the table, it is shown that the Allen Bradley PLCs had a 100% success rate in finding a message with the correct message length and an average similarity of 100%. The Modicon, however, had 24 messages out of 8,800 requests that did not exist in Similo's database. However, with a level of accuracy of 99.99%, there were no errors on the engineering software. In addition to the packet level accuracy and the function level accuracy, a mock-up forensic analysis was performed for denial of engineering operation attack 1 and denial of engineering operation attack 2. For attack 1, a ladder logic program was developed to simulate an open-loop traffic light system. In this program, there were 3 timers, one for each color. For the green light, the preset timer was set to 20 seconds. Both of these attacks utilized a man-in-the-middle attack by utilizing ARP poisoning over ettercap. Afterwards, forensic analysis was performed utilizing Similo, and the traffic was reviewed between the engineering software and the attacker, and between the attacker and the PLC. For the forensic analysis between the PLC and the attacker, the first PCAP file was loaded into Similo, then uploaded from the engineering software, resulting in the decompiled ladder logic as shown in the first figure. Notice that the PLC is reporting the preset time as 80 seconds. For the forensic analysis between the attacker and the engineering software, the second PCAP file was loaded into Similo, then uploaded again from the engineering software, resulting in the decompiled ladder logic as shown in the second figure. Notice that this time the attacker has changed the preset time back to 20 seconds before sending it back to the engineer. For denial of engineering operations attack 2, the attack was simulated as described. When an upload request was sent from the engineering software, the attacker modified the valid instruction data and replaces it with noise. In this case, the instructions were placed with all Fs. Looking at the forensic analysis provided by the network traffic through Similo, the following is shown. A request message is sent from the engineering software. The response from the PLC to the attacker shows the original response. Note the area labeled original instruction. The response between the attacker and the engineering station, however, shows that this data was modified. From the paper, by tampering with the original instruction, the decompiler was unable to decompile the message and effectively crashed, as the decompiler was unable to respond. Because of the sensitivity of an attack on an industrial control system, ICS cybersecurity has been researched by many. Valentine and others discuss application-level vulnerabilities in SCADA systems. Kottler and others discuss a formal verification of ladder logic programs using nusmv. Beresford and others provided research on replay attacks on the S7 protocol. Senthivel and others identified the denial of engineering operation attacks and created Lattice, the decompiler that was discussed earlier. Links to these papers can also be found below. While the primary goal of industrial cybersecurity is to prevent an attack from occurring, Similo has proven that by capturing network traffic, performing a forensic analysis to determine the effects are not only possible, but that with the right tool, the process can be both simple and accurate. Thanks for watching.